Now we have the final question, question G. Let's assume a ridge regression estimator, and we are asked to draw a plot that shows how the training error, the test error, the squared bias, the variance of the predictor, the variance of the reducible error depend on the ridge parameter lambda. First of all, the reducible error, of course, by definition does not depend on lambda, so it is constant. Then we have the variance, for instance, of the estimator. And concerning the variance of the estimator, of course, when you apply a shrinkage method, as long as the shrinking parameter is increasing, so you are shrinking more and more, this reduces the effective degrees of freedom of your regression function, and therefore you are reducing the variance. At the same time, this is going to increase the bias because you are less flexible, and so this blue line, that is the square bias, is going to increase. And the mean square error on the test data, okay, that is this red line, will usually have a minimum, because here you have, this is constant, okay, this is going down, this is going up, and therefore it is quite common that you will have a minimum at some point, and this minimum would correspond to the optimal value of the shrinkage parameter lambda. Of course, it may not be easy to find it, because here I'm plotting the theoretical value of this function, but in practice you do not know this, and you have to estimate by some of the methods that we have been studying during the course. Finally, we have the mean square error on training data, and here the point is that if you are not shrinking, then you are very flexible, and in the end you could even succeed in fitting all the data if your model is rich enough, and therefore you have that this is going to decrease as long as lambda gets smaller, okay, and therefore this is not a good criterion to choose the optimal value of lambda, because it will always suggest you that you should be using a very small shrinkage parameter, or you should not shrink at all if you look just at the training error. Okay. The final exercise in this exam was a list of true-false questions. So just let's see them together. First question: nearest neighbor regression can be pretty good for small n, size of the training set, and large p, number of predictors. Well, it is just the opposite, I would say, because for nearest neighbor to work well, you should have enough data in such a way that your data are quite dense, because if the data are dense, you can rely on the neighbors in order to get a reliable estimate of the function in a neighborhood. And if the number of predictors is large, if p is large, it is very difficult to have dense data, because we have seen that there is the curse of dimensionality, while if you have p equal to 1 or p equal to 2, it could be relatively easy to fill the space in such a way that when you consider some x, you have enough data around that point, and you can use them as neighbors in order to estimate the function. But when p is large, the number of data grows very, very fast, and this is the very reason of the curse of dimensionality, and therefore this is false. Okay. B. In linear least squares regression, if you know the variance of the irreducible error, and you have a parameter whose true value is 0, then its estimate over 1.96, its standard error, is a standardized normal variable. As a matter of fact, if beta is equal to 0, and moreover, you should also assume that the model is linear, and you should also assume that the errors are Gaussian, something that is not specified here. But anyway, there is also another mistake, because under all these assumptions, that is that the true model is linear and that the errors are normally distributed, in this case, if you standardize beta hat, you have to take beta hat minus its expectation, that is 0, over its standard error, that is the standard, over its standard deviation, which in this case is just the standard error of beta I, and this would be a normalized Gaussian variable. But as you can see, there is no 1.96 around, therefore this is false. So it is false due to the 1.96, but also you should have specified that the errors were Gaussian, and that the true model was consistent with your least squares estimation method. Question C. For classification problems, logistic regression is more appropriate than linear regression because it does not produce probabilities than 0 or bigger than 1. Well said. Yes, that's true. So this is a clear true response. D. Let n denote the number of observations, then leave one out cross-validation coincides with k-fold cross-validation with k equal to n. Yes, in this case, the number of folds when you are resorting to leave one out is just equal to the number of data. So k equal to n leads to leave one out cross-validation. True. E. If the tuning parameter lambda is large enough, the lasso will include only a subset of the p-predictors in the final model. Okay, we have already said this, that the lasso has this property that the shrinkage becomes complete, so that so long as you are increasing lambda, you will see that more and more estimated parameters collapse to 0. That's true. Okay. A natural cubic spline extrapolates quadratically beyond the boundary knots. This is false, because you know that extrapolation of cubic splines is linearly beyond the boundary knots. So false. The result of random forests and boosting can be difficult to interpret. This is true. And this was an observation that that was made, that simple trees are less accurate than more sophisticated methods like random forests and boosting. But the advantage of simple trees that, although less accurate, they are easy to understand. So they're more interpretable. But if you want accurate prediction, then you should take into account random forests and boosting, although they are more difficult to interpret. Among all separating hyperplanes, the maximal marginal classifier is the one that makes the biggest gap or margin between the two classes. Yes, if you have the possibility of finding a separating hyperplane, and you know that this may not happen in some cases, so there are classification problems that such that the data, your training data, are not linearly separable. But if you can separate by hyperplane, then the definition of maximal marginal classifier is that makes the biggest gap or margin between the two classes. I, k-means, is guaranteed to achieve a globally optimal solution. So I will not go into the definition of the cost function that we gave during the lecture, but you should remember that for that cost function, the approach of k-means is a greedy one. So at each step, it tries to make as much progress as possible, but in this way, it could well happen that it is stuck in some solution that is locally optimal but not globally optimal. Therefore, there is no guarantee that k-means will achieve a globally optimal solution, and we also gave examples. So we applied k-means with different initializations, and by changing the initialization, you can get different final solutions, and we showed that this can happen. So in some cases you found just the same solution starting with different initial values. In other cases you could find a different solution. Of course, you can choose the best one if you are running the algorithm more times in order to be sure that or have a good confidence that you are finding the optimal solution. But if you run it just once, there is no guarantee that you will find a globally optimal solution. Final question: if x and y are jointly normal with the same mean and variance and positive correlation, so these are a couple of random variables, and they have the same marginal distribution, but they are positively correlated, then it happens that y minus x is negatively correlated with x. You should remember that in the final chapter on the fallacies of learning, we discussed just this problem. So x and y could be the performance, for instance, of a class in a school. So you just administrate a test at some point, then you administrate the test again, and for instance, assume that there was no improvement. It might be because for some reason the pupils did not improve, or for instance the second test was administered so close to the first one that there was no time to have a real improvement. In this case, the marginal distribution is obviously the same, because you have the same pupils that are repeating a test. Of course, the results are different because there is some randomness. So some pupil could be luckier or less lucky when repeating the test, and but of course, if a student is clever, is generally clever, his or her scores will be similar in the two, not identical, but they will be similar. Okay, at this point you are computing the difference, so you are asking, but what does it happen if I had a student with a good score in the first test, which is x, then I look at y minus x, that is to the improvement, and it happens, we demonstrated this, that under the given assumptions, the students that had the best results in the first test are more likely to have a negative improvement. On the other hand, the ones that had bad results in the first test, they are more likely to have a positive improvement. So if you look at the improvement y minus x and study and estimate its correlation with x, you will find that this is negatively correlated with x. And this is often seen as a sign of convergence. So the teacher or the school director will be happy because it is seen that the ones that had bad marks are performing better, and at the same time it happens that the ones with very good marks they are not keeping with the initial results. But of course you are saying that this is convergence, and you could give some merit to the teachers, for instance, but under these assumptions this happens even if the distribution of y and x are just the same, so the marginal distributions are the same. This is just one of the effects of the regression to the mean that we studied in the final chapter of the course. And so this is true, and okay, we can stop here with this exam.